let's talk about the measurement of light. And this corresponds to the chapters 7 and 17 in our textbook. And let's just review two key terms here before we jump into figuring out how to calculate these numbers. First of all, luminous intensity is the amount of light coming out of a light source in a particular direction. In this case, luminous intensity coming down toward the table. The other number that we need to know is illuminance, and that is the amount of light landing on a surface. Illuminance is measured in lux or foot candles here in the United States, and everywhere apparently it's measured in luminous intensity is measured in candela. And these numbers, you might think, well, how would I know? Well, you can get data from product manufacturers. They will generally publish data about the directional strength of the light source that they are selling. And this can be by either the lamp manufacturer or the luminaire manufacturer. And what I'm talking about here, each luminaire, and these are very similar looking luminaires from Urco, a German company. Some have a light distribution that is quite soft and quite limited. It doesn't throw light very far. And as you can see, these patterns from each of these light sources are quite different. Oops. And these, there are sort of an infinite variety depending on what you're trying to do with the light. This light, for example, will throw a lot of light sideways, but basically nothing down. This one's throwing some light up. This one's throwing it in a much more soft kind of cone. Anyway, you can get photometric reports from pretty much any manufacturer, although sometimes you do have to kind of dig around for them. And often they will be either in a polar candela plot or candle power distribution plot, or they will sometimes be in a chart. And if you think about it, even just choosing different lamps, each lamp is going to have a very different light output. Something like a PAR lamp, a PAR lamp, is going to have a very directional light. It's going to be omnidirectional and can be quite narrow in its beam spread. Whereas our familiar A15 or A19, that is going to send light pretty much omnidirectional. And this information, by the way, you can find this information on the product, on the box from the product, along with a lot of other things, the overall light output, which is measured in lumens, and the color temperature, and the color rendering, again, depending on the product and its rating. So another key concept here for our lighting calculation is the inverse square law, which is to say that the farther away you get, for every unit you get away, the brightness that is landing on a surface is decreased by 1/4. It's exponential. 1 or 2 squared, I guess, if you double the distance, is 1/4 the strength. So how does that translate into kind of architectural settings? Well, if you double your ceiling height, you will have 1/4 the strength, the quantity of light landing on the floor. So let's say you have a whole bunch of recessed cans in a room with 8-foot ceilings, and they're generating 12-foot candles on the floor. How many foot candles will you have if you double the ceiling height? Well, we can figure that out without even a calculator, probably. The inverse square law says if we double the distance, we have 1/4 of the light. So 1/4 of 12 is 3 foot candles. And that means, and here's the math right here, 3/4, 12 quarters is 3. Now, how many fixtures will you need to add to get back to that same 12-foot candles? Well, you have a lot. So now 10-foot candles, 10 cans are just producing 3-foot candles. If you want to get back up to 12, you probably need 4 times as many. You need 40. So you have to go and buy another 30 and also have to drop those onto your ceiling plan. Now, there are other ways to do all this. You can measure light as it exists in situ. There are a couple of different apps that you can use if you have a smartphone. One of them measures luminance. This is a light meter by Polyanki, which I found, which is free. So I'm going with the free stuff here. And we've already tried this Good Sleep app, which does a fairly good job, probably within 10% of measuring the color temperature. So let's talk about design verification. This is the part where we have to do some math, and you're going to love it. First of all, we're going to do some easy math. There are some rules of thumb, which are pretty straightforward, but then we're going to do some calculations. So first of all, let's start with our rules of thumb. And downlighting rules of thumb, when you're laying out your ceiling plan, say in schematic design, how many downlights should you put in your ceiling just to get light on the floor in your corridors? Well, basically there is a formula, which is the spacing, S equals what's called the spacing ratio times the mounting height. Now, the default value, the sort of rule of thumb, is the spacing ratio is 1. So if you have 8-foot ceilings, you end up with spacing your recessed light fixtures 8 feet apart. Now, this works also if you are dangling fixtures from the ceiling, dangling point source fixtures. And this really only works for things like recessed cans. What you will find when you look at actual manufacturers' data is that they publish the spacing ratio in their data, and then you can plunk that into the calculation and get an exact spacing. But for schematics, you just want a general idea. Now, you can also use a rule of thumb for wall washing. The rule of thumb here is the distance from the wall is 1/4 of the wall height. And that's pretty straightforward. You have a 12-foot wall. You should space the light fixtures, the recessed cans or other recessed lighting, 1/4 of that, so 3 feet apart, both and 3 feet from the wall. Grazing lighting is very similar. Grazing lighting is when you want to bring out the texture of the wall. That's 1/8 of the wall height. And again, if you have a 12-foot ceiling, that means you're going to be having a D value, the distance from the wall, of 12/8, or 1.5 feet. And then the spacing ratio, again, will be the same. So if I had a problem, and again, this is a big hint here, maybe this is something we'd even see on our test, I don't know. If we had a given ceiling height of 16 feet, how far apart would we space our downlights? Well, we'd space them, based on our rule of thumb of 1, we'd space them 16 feet apart. This, of course, is probably not drawn to scale. It's an old plan. I don't even remember where I dug it up. If you wanted to figure out the wall washer distance from the wall, it's 1/4 of the distance from the wall. So this looks about right. 1/4 is going to be 4 feet, and then they'll be 4 feet apart. And then the grazing lighting, come back. The grazing lighting will be the same. 1/8 of the wall heights now. We're 2 feet from the wall, and in theory, 2 feet apart, although I didn't redraw them. There are many other rules of thumb, which are great if you are in your studio or at work and you're just kind of trying to figure out, well, wait, I want some, a linear slot, say on a wall or something like that. How far apart should it be? 1/4 the height. That's a pretty easy one. Will that be exactly right? No, that doesn't involve a real product. And there are products you can buy which can be mounted closer to the wall and still get a very effective light distribution. Again, these are just rules of thumb as you're working through your projects. Same if you want a luminous ceiling. How many fixtures? Just ballpark it. Well, you can calculate D, the distance from the ceiling, and the spacing ratio is related to that. So obviously, if you're in a situation where you don't have much ceiling height that you can drop, then you're going to have a lot more light fixtures to get an even lighting effect. Even things like a cove or a slot, they can operate on general rules of thumb. In this case, 1/6 of the span that you're trying to light. Again, there are fixtures out there that can throw light farther, but this gives you a general idea. Now, linear lights, these are basically as similar as this to the ceiling slot, except they're coming from the side of the wall. Finally, there is a handy-dandy chart in the textbook, which indicates, first of all, the ideal mounting height for a spotlight that you're using to light a painting on a wall. And all you need to know is the ceiling height and the height of the painting. Now, in this case, this is the typical mounting height, the kind of graphic standards of mounting heights for paintings, 5'3" off of the floor to the center line of the painting. Then if you have a 16-foot ceiling, you just measure how far out the adjustable light will be. And if you mount the adjustable light there, it will get you the perfect 30-degree angle. This 30-degree angle is ideal because it avoids any glare. You could, of course, go into Revit and draw it all up and make the exact angle 30 degrees and get your calculations, and you'll be perfect. But in this case, it just for rule of thumb, just so we know where in the ceiling plan to put those adjustable spotlights. So when you have actual photometrics, that's when you can do a mathematical calculation. Let's take a look at some of those. First of all, there are 3 different calculations that we would probably do as an interior designer. I would like to encourage you to not do too many calculations if you are finding that they're getting kind of complicated. However, quite frequently, since you are often designing highlights in your space, it's not a bad idea to at least know how to know what to ask for from your lighting designer and how to do these basic calculations. So first of all, let's start with a point calculation. And typically this is something like you're trying to light a painting or a light sculpture, some kind of architectural element, perhaps a very interesting column or a niche. There may be 1 or 2 directional luminaires. So it's a simple calculation, things that you're really trying to highlight and drop a lot of light on. And the point source formula is pretty straightforward. The illuminance in foot candles equals the candle power in candela, and that is the amount of light coming out of that light source right onto whatever it is you're trying to light. So you do have to take into account the angle that the fixture is mounted at. Anyway, that candle power divided by the distance squared. So what does all that mean? Well, let's draw it up. Okay, that's really the start of a single point source calculation. Here's an example. You're trying to light a mural that's on a floor. You're trying to light it from a single spotlight, a single downlight above it in the ceiling, just a recessed can. But you know you're going to buy a special lamp to put into that can because you need a high degree of control of photometrics because you want that to be really bright compared to the adjacent floor. Well, what you do first, you draw it up. So I've drawn up 14-foot ceiling height. I put in a light fixture. I figured out that the diameter of my mural is whatever it is, 5 feet or something. So it ends up with a 20-degree angle. That angle is really the thing that makes the difference, because now I can go shopping. I can look up a lamp, and I looked this up in lamps or lightbulbs.com, I believe. And the link is further on in the lecture here. And I can sort in lightbulbs.com for an exact angle. In this case, the beam angle, I guess I wanted 30 degrees. And it will tell me this. Sometimes it will say center beam candle power. In this case, it says CBCP, which happens to mean center beam candle power. I wish they would spell it out. That would make my life better, but you know, what you can't get everything. Anyway, and now I have all my numbers. I have the height, I have the center beam candle power, and I can just plunk them right into the formula. And what I get is 3,460 candela divided by 10 squared, and I get 34.6 foot candles. See, that wasn't so bad. But when it does get bad, it gets really bad. When you have a light source, which is not, the center of the candle beam is not perpendicular to the object you're trying to light, then you have to adjust based on the cosine of theta. And then it gets a little more difficult. Basically, you're taking that same calculation and you're just multiplying it times that cosine. Another concept about lighting paintings, and here I've drawn up a diagram of lighting a painting from a recessed can in the ceiling. I've done my calculation of the angle. I know my ceiling height. And I also have to consider that I probably will want 2 light sources on this painting. The problem with one in the center is with a bigger painting, the human being observing the painting may get into the light range. It might cause a shadow. So, and a big painting, it's better to have 2 lights on it anyway. So as an example, this one, if it gives 5 foot candles for one fixture, you can add those together. It is additive. So I have 2, so I have a total of 10 foot candles. And you are trying to create a light level on the painting that is at least triple the background light level. Double is probably pretty common, but triple is the ideal. And as mentioned, this is the calculation where the distance is the distance to the center of this painting, but I would have to multiply my result times the cosine of theta in order to get my light level. So what about lighting an entire room? This is when you have multiple fixtures, and the traditional way to do this is to use a method called the zonal cavity, or sometimes it's called the lumen method. This takes into account quite a few different factors because now you are lighting a 3-dimensional volume. There's a lot to think about, including the ratio of the room cavity that you're lighting, what's called the coefficient of utilization for luminaires, light loss factors, lamp lumen depreciation, lamps burn less brightly over time, and even things like luminaire dirt depreciation. These are all numbers you can get by looking up data in the luminaire manufacturer's information. But sadly, I know you're all looking forward to really digging into some numbers, but we won't do this by hand. You do need to know that it exists and that it can be done. And typically you're going to call up your friendly neighborhood manufacturer's rep or a lighting designer or an electrical engineer to help you out with these. Now, the basic formula for this is the light level in foot candles. That's what we're always shooting for. Is the number of lamps times the initial lamp lumens times the light loss factor times the coefficient of utilization divided by the area. That sounds simple, doesn't it? And to give you a visual on this, you're looking at a space, you're looking at the things in the space and the kind of reflectance that each has and how that affects the light bouncing around in the room. And many different materials. Some of them have quite a surprising reflectance. For example, you would think wood, oh, that must be, not very reflective, but birch could be quite reflective, even as much as a light-colored paint, whereas something like walnut could be extremely absorptive, very unreflective. And these numbers are available in interior design graphic standards or from product manufacturers. And here are some more reflectances. Again, white paint, that's probably going to be pretty bright. But even things like masonry, it can be surprisingly reflective depending on if it's polished and the kind of color balance inside it. And the room cavity ratio, again, this is straight out of the book, is looking at the proportions of the room. That's really all you need to know. And there's a form which again is in the book that you can kind of fill out all the bits and pieces, but frankly that's a little bit much for our purposes. It's just a little more complicated. If you find that you need to do this by hand, then you're probably in over your head. But you do need to know when you're hiring somebody what they're doing and what you're asking them to do. In this case, you're asking them to do the room cavity, the lumen method calculation. So, and one thing that you also should be aware of is that there are standards for light levels in different spaces. These are all from the IESNA, the Illuminating Engineering Society of North America, the publishers of our fun competition that we took part in. And the thing to note here is that these are guidelines. They are not, exact, and things like public spaces where you don't need a lot of visual acuity, you just need enough light so that you don't walk into other people and walk into walls. 3-foot candles is a very reasonable level that doesn't take into account things like, is it a bright day in a highly daylit space, or is it in an evening in a very dark space? There are many other things that come in as factors, but basically the more acuity you need, the more complicated the visual task, the more light you need. And you can just look these up in the book, but and this is provided on Canvas in our documents. But the highest numbers that you're probably going to be seeing in your professional life are probably somewhere from 50 to 100-foot candles. Something like a kitchen for senior citizens, they're going to need a lot of light. They're going to need about 100-foot candles. Beyond that, you're probably looking at an industrial sort of use. And there are endless lists of kind of recommended levels here. A hospital operating room can need 300-foot candles. You would want people to not be fumbling in the dark there. Whereas something like a kitchen, that is going to be variable based on the age of the people using it. So let's take a look at an online calculator, which we can use to make our calculations without stressing out too much. You can just click on this link to follow it, and it will open up in a new window. So here, this tool is really, really handy. First of all, you can display it in any number of different ways. You can type in different lengths for our room. So for instance, if we wanted to do our classroom, I believe it's about 40 by 25. And yeah, the ceilings are about 11, 12 feet, I think 11 feet. We can define where the work plane is, typically 30 inches off the floor. We can also tell it to have a 2x2 or 2x4 ceiling, and it will draw it in there. You can type in numbers for the ceiling, the walls, and the floors. Now we'll just go for the default values. You can also tell it how many foot candles you want. 30-foot candles, interesting enough, is probably about what they were shooting for when the building was new. Finally, you have to come down here and find a light fixture. This is actually the hardest part, because if you click on that, it opens up a window with sort of a million light fixtures from quite a few different companies, actually. Although I think they're all kind of owned by each other. But Lithonia is a very big company, and they have a million light fixtures. So I thought I'd just make it easy. Just go to Lithonia and a commercial indoor, and we'll just go with a panel, LED flat panel. Let's pick something simple here. And I think a 2x2 is probably what we want. I'm going to go with the slightly higher lumen output, 33 lumens. Again, if you are doing this and you are the only one doing it, you should just call up the Lithonia lighting manufacturer's rep. They'll tell you what you need, because there are many subtle differences between all these fixtures that I couldn't even begin to tell you. So I'll select that, and what you'll see is it will put the spacing here into the drawing. If you change the light level, let's say we're going to save some energy, we're going to make it 20-foot candles. It will adjust the amount of lights. Or if you make this 60-foot candles, again, it will put a whole bunch more. You can force it to have a specific spacing if you want. I'm going to stick with 30-foot candles, and there you go. You get a nice result on the ceiling. And of course, you could totally add different light sources on here and get yourself a real nice set of comparisons that you can show your client. And finally, you can add some project information if you want, and then you can print this puppy out or send it to somebody. So the last type of calculation is actually the easiest, but it's kind of also the most irritating one, and this is what is required by the building code here in Massachusetts. It's called the lighting power density loading, and it typically is going to be really just a number based on your project type. This is right out of the building code here, but this chart is table, 1308.6.2.1, which I'm sure you've run across. And basically, it's just saying this is the maximum power you are allowed to use for lighting in your project. So let's say you're working on a hotel. You can use 1.7 watts per square foot. Whereas if you're doing a parking garage, they are only allowing you to have 0.3 watts per square foot. This is why we have really super high efficiency lighting in somewhere like a parking lot, whereas you are allowed to have much more elaborate lighting in something like a retail setting. They really allow you a lot of power density there. Does not have anything to do with the quality of the lighting. However, the higher the lighting power density you have, it stands to reason that you're going to have a much higher electric bill because you're using more power per square foot. In something like a retail setting, that's probably fine. In things like schools, they're often shooting for a lower power density than the kind of maximum allowed by code, just because these numbers are actually not particularly aggressive or sustainable. So in summary about our lighting calculations, the biggest thing is that you should know the appropriate light levels that you're shooting for. Is it 5-foot candles, 15-foot candles, 50-foot candles, or 500-foot candles? You should know what those numbers are and be familiar. You would probably in your own office life do some point source calculations for critical applications. Let's say you have a painting or a sculpture. You would by all means do that calculation. It's not that hard. But I would absolutely recommend calling the manufacturer's reps for situations where you're trying to use something like fluorescent or troffer type of application. You're not going to do that calculations. There's way too many options. Any basically acoustical ceiling system is going to be too complicated for you to figure out. Finally, when would you call a lighting designer as opposed to an electrical engineer? Well, that is when you're trying to create a lighting effect that is dramatic. Any engineer can lay out a open office plan with a boring 2x2 grid and give you a calculation. But can you make it interesting? Can you make it dramatic? Do you have unusual materials? Do you have some unusual effect? Well, that's when you'd call a lighting designer. Finally, I have provided a couple of test problems here. I'd like you all to take a look at them and see if you can figure them out. Just write down your answers, and I'll have a spot on Canvas where you can upload it. And of course, I will try in our open class time, you will be able to ask me a question. And I threw a real doozy in there, but hopefully if you understood the lecture, you'll be able to do these problems. And if you can do these problems, I'm not saying I'm going to have problems like this on the exam, but, well, maybe I'm saying that I am going to have problems like this on the exam. So you should really give them a try. This is part of your practice. There also will be a practice exam on Canvas for you to take. It is not worth any points, but you can take that. I would strongly recommend that you go through that practice exam. This has been an unusual semester, and I think we need to make sure that everybody remembers what we learned from the earlier part of the semester. And frankly, a lot of this stuff are very detailed items from the book. So if you haven't read the book yet, I would read that before taking the practice exam. Or some people like to take the exam first to find out what they should be paying attention to in the book. I don't care one way or the other. I just really want you to know these concepts and these terms and terminology and techniques.